So the problem I want to look at is section 5.4, number 68. It's called a static equilibrium problem, and we have a weight of 800 pounds suspended from two cables. So here's the first cable and the second cable, as shown in this figure. And when we have pounds, we don't have to worry about gravity because this is considered 800 pounds of force. So we're already in units of force when we're in English units. So the first thing we need to do is draw a picture that will be more helpful to us. So we think of that load as what's called a point load, and we just draw a little point to represent the box. And then we show that there's 800 pounds pulling straight down on the cables because of the weight of the box. So then we need to look at what angles the cables are at, and the first one's at an angle of 35 degrees from the horizontal. So this angle is 35 degrees, so we also know this angle is 35 degrees. And this is a force, a tension acting, pulling upward and outward on this box. So then the second cable is at an angle of 50 degrees from the horizontal, so we know that this angle is also 50 degrees. So I'm going to name these vectors T1 and T2, just so I can tell them apart. And then let's talk a little bit about T1 and T2. So we know that T1 is going left and then up, so it's going to have a negative I coordinate and a positive J coordinate. So we just have to find out what these numbers are for how big is this force. And then T2 is going to have a positive I coordinate and a positive J coordinate because it's going to the right and up. So what we're trying to do is say, how big do T1 and T2 have to be to balance out this 800 pounds that's pulling downwards? So this is the picture that we're going to use. And now we're going to break down T1. So T1 looks like this. Vector. And we're going to break it down into two components. This component is going to be T1x. And then you can see that if we add T1y, that T1x plus T1y equals vector T1 by vector addition, right? And now we know this angle with the horizontal is 35 degrees. So does it make sense that the cosine of 35 degrees is going to be the magnitude of the T1x vector over the magnitude of the T1 vector, because you can see we've created a triangle. And the cosine of the angle is going to be the adjacent side over the hypotenuse. But we have to use magnitudes here because vectors have direction. So we can't divide something with a direction by something with a direction, so we have to divide the magnitudes. So it looks like the magnitude of T1x is magnitude of T1 times the cosine of 35 degrees. So that's going to be the x component, and we can see that it's pointing in the negative x direction. So now let's look at T1y and think about the sine of 35 degrees. And the sine of 35 degrees is going to be the magnitude of T1y over the magnitude of T1. So can you see that T1 times the sine of 35 degrees is going to give me the magnitude of T1y. So now I can write vector T1 as the magnitude of T1x cosine of 35 degrees, but that's pointing in the negative I hat direction because it's pointing to the left, plus magnitude of T1 sine of 35 degrees, and that's going to be my j hat component. So that's vector t1 written in its components. So now let's look at vector t2. So vector t2 looked like this, and it had an angle of 50 degrees. And we can see that this is t2x vector. This is t2y vector. And so t2x vector addition with t2y equals vector t2. So now we're going to do the same thing where we're going to say the cosine of 50 degrees is the magnitude of t2x over the magnitude of t2. So magnitude of t2x must be magnitude of t2 cosine 50 degrees sorry about that. So t2x is going to be magnitude of t2 times the cosine of 50 degrees. And then the sine of 50 degrees is going to be magnitude of t2y over magnitude of t2. So magnitude of t2y is going to be magnitude t2 sine 50 degrees. And we decided at the beginning that t2 is going in the positive x direction. So t2 cosine 50 degrees I hat and the positive j direction plus magnitude t2 sine 50 degrees j hat. Well, static equilibrium means the sum of all the force vectors is the zero vector. So if I take the t1 vector plus the t2 vector plus the force vector from the box, it has to equal the zero vector. So we decided t1 is magnitude t1 cosine 35 degrees I hat plus magnitude t1 sine 35 degrees j hat plus t2 is magnitude t2 cosine 50 degrees I hat plus magnitude t2 sine of 50 degrees j hat. And then the force from the box is negative 800 in the j hat direction. It's going straight downward. So here is the equation that we need to solve. And it's actually two equations. If you just look at the I hat terms, they have to add up to 0. So t1 cosine 35 degrees plus magnitude t1 sine, whoops, let me erase that. So that's going to be magnitude t2 cosine 50 degrees. So this I term and this I term. That's all the I terms there are, so those have to add up to 0. So then we have the j hat terms. So magnitude t1 sine 35 degrees plus magnitude t2 cosine, magnitude of t2 sine 50 degrees minus 800 has to equal 0. So that's this j term, this j term, and this j term. So now it's not the zero vector. Up here it was the zero vector. But now I'm just looking component by component. So it could save you a lot of writing if you say, let me let the magnitude of t1 equal a, and the magnitude of t2 equal b. So then let me rewrite these equations as a times the cosine of 35 degrees plus b times the cosine of 50 degrees equals 0. and then A sine of 35 degrees plus B sine of 50 degrees. I'm going to put the 800 on the other side, equals 800. So now do you recognize this as a system of equations, two equations with two unknowns, A and B? So one way of solving the equations is substitution, but I'll just warn you that's pretty awful. And I'm going to show you elimination, which is bad enough. Or you can also call it addition method. So I see I have A times sine of 35 and cosine of 35. So if I want the A's to cancel out, I'm going to need to multiply by negative sine of 35 degrees on both sides here. So then I'll have an A sine 35 cosine 35. And I'm going to need to multiply by positive cosine 35 degrees on the second equation. So now the A terms are going to cancel. I have A cosine 35 sine 35 negative and A cos 35 sine 35 positive, so those are going to cancel. Then I'm going to have minus B sine of 35 degrees cosine of 50 degrees as I distribute. And then I'm going to have plus B cosine of 35 degrees sine of 50 degrees. And that's going to equal 800 times the cosine of 35 degrees. So now hopefully you can see how to solve for B. Factor out B, and you get B cosine 35 sine 50 minus sine 35 cosine 50 equals 800 cosine 35 degrees. So to solve for B, I'm going to divide 800 times the cosine of 35 degrees by cosine 35 degrees, sine 50 degrees, minus sine 35 degrees, cosine 50 degrees. And I'm going to get a decimal approximation when I do this. And I get about 657.8 pounds. So don't forget the units of the pounds. And then I can go back up to equation 1 and say, well, A times the cosine of 35 degrees plus B times the cosine of 50 degrees equals 0. So it must be true that A cosine 35 degrees equals negative B cosine of 50. And then divide both sides by cosine of 35 degrees to get A, and I get about 516.2 pounds for A. So that's how I would like to see you do an engineering statics problem. And the tension in the two cables is what we were after. So the one pointing to the left, which is magnitude T1, is 516.2 pounds. And magnitude of T2 is the 657.8 pounds. So let me know if you still have questions.